Came over from Canada. I've been working in shipbuilding since the early 90s on the Canadian Patrol Frigate project. I'm not a naval architect by trade, but I have worked in shipbuilding as recently as now. And we'll be, just let me get the slides up. Do a screen share. We'll be introducing the Gibbs and Cox team members who have worked on our small autonomous underwater or unmanned surface vessel, the environmentally powered modular autonomous platform system, otherwise known as EMAPS. So myself, Alan Stoats, I'm the Director of Maritime Autonomy at Gibbs and Cox here in Australia. I've been here for 2 years, came across to work specifically on this project, and have been working with a very talented group of engineers. My boss, Levi Catton, isn't here tonight, but Levi was the original brain behind the EMAPS concept. And the team that will be presenting tonight, Torsten, Eliah, and Michael, are the three primary engineers who've been working on and developing the design that we'll be talking about. Torsten has been with the project since before its outset and worked on the concept design, has his partial patent on the AMA retraction system for the deployment of the side hulls. Eli Cameron was with us for a few months as a undergraduate student at AMC, finished his degree last year and joined the project full time earlier this year. And Michael Reilly has been with the project for the past 2 years, has developed the full electrical solution for the EMAPS system. So we started the EMAPS as a concept design in 2022 with the premise that it was an uncrewed surface vessel, remotely and/or autonomously controlled, environmentally powered, with a significant modular payload capacity and the ability to transport it and launch and recover by road. So our initial design constraints, which Torsten will talk about in greater length, were driven by those fundamental principles. We wanted a workboat that had the flexibility to be used in almost any application by almost anybody, almost anywhere. We started the EMAPS prototype design in 2023 and went through all the normal activities of looking at NSCV rules, understanding that we're designing a vessel that doesn't strictly adhere and can't, in some cases, adhere to what an NSCV calls out. Similarly, we engaged with AMSA and went down the road of trying to understand and navigate how to design and build a vessel that we can operate under AMSA's regulatory regime. So the AMSA was very helpful in this. They recognize and acknowledge that this is a new concept of operating vessels, and they're working quite hard to develop their regime and protocols for the design, production, and operation of uncrewed surface vessels. We took all of those inputs and developed the design constraints and developed a detailed and production design, which manifested some of the unique things about this boat that were driven by those design constraints and the facts that it's not designed around a human operator being on board. It's designed around the premise that it's out on the water operating without anybody on board. And that led to some fundamentally interesting design challenges and some unique solutions that we'll talk about in greater length. We went through all of the normal things that you would go through in designing a boat, allocating weight and margins and looking at stability. A lot of the process that we went through is exactly the same as what you would go through if you were designing a crewed vessel, but with some fundamentally different underlying principles that drove how the design unfolded. And we've gone through the process of engaging and working with AMSA certified surveyors to inspect the boat as it was manufactured, to ensure that we weren't breaking any of the rules and design principles that you would expect in a vessel that you want to safely operate in Australian waters. So having gone through all of that, our first boat floated in October 2023, so a little bit less than a year ago. That picture on the side of the screen was taken up in Gold Coast. And we went into pre-production, built our design, redesigned certain aspects of the boat, changed our lamination schedule, and started into our test and evaluation program this year. Through that evolution, some of the lessons that we had learned in putting that first boat to work led to design changes. We refitted and built new hulls and went through some of the other design changes that were needed to make the boat more manufacturable and easier to operate and maintain. But fundamentally, there were differences in how we approached the design, but there were a lot of similarities in how we went through the design process and some of the conclusions that we came to. So just to highlight some of those guiding principles, AMSA, their principles for autonomous boats and uncrewed boats, whether they're remote controlled or autonomous, is that they must be as safe as manned vessels. Safety is first, and that's been the main consideration in any of our design changes and design implementations has been to make the boat safe to operate. The risks to safety of people, other vessels, and the environment must be appropriately addressed. So we weren't putting anything into the boat that would cause environmental concerns. We ensure that if we do have issue with the boat, that it's not going to cause problem for other operators on Australian waterways. And ultimately, the owner and or master is responsible for the safety standards, which are reflected in the design and how we operate the vessel. So we've gone through, on the one end, designing the boat, but we've also considered the factors of what does an operator who's sitting at a laptop control need to be able to safely operate these vessels. It's a different problem, fundamentally different from operating a vessel when you're sitting at the helm, but ultimately, a lot of the same considerations. You need 360-degree visibility. And you need to be able to understand the environment around you and navigate safely. And from an AMSA perspective, if they understand that you understand those principles, they're going to work with you pretty closely to ensure that that regulatory path is relatively easily navigated. And they have been really good about that. Ultimately, at this point, with the EMAPS vessel, we're in the process of seeking our application for exemption to certification. We have a temporary operations permit at the moment for 90-day operations, and that will roll over into that exemption from certifications by the end of the year. The other organizations that we had to consider were IMO, which is going through the same journey of trying to understand what does automation mean to maritime surface ships. And they're looking at it from the large vessel context, but a lot of the principles apply, and they apply equally to small vessels, just in that context of vessels under certain sizes and speeds. And they're working through that process with the Maritime Autonomous Surface Ships Code, which is intended to take effect in 2025. And again, the IMO constraints on how do you ensure you have a bridge watch that's maintaining that situational awareness. We need to be able to do that in an autonomous boat, the same as we do in a crewed vessel, and that is reflected in some of the design decisions that were made in the EMAPS vessel. So those considerations drove the design constraints that Torsten's going to talk about, the crude design elements and different approaches that we took in the design of the boat, and the weight allocations and system locations that Eli is going to talk about, and how do you operate and control all of those systems remotely that usually you would have a crew member on board to operate on your behalf. So with that, I'll hand over to Torsten, who will talk you through some of the design constraints.
Thanks, Alan. As Alan mentioned, I'm just going to spend a bit of time talking on some of the major design constraints of EMAPS and some of the challenges we faced with these constraints, and then just the lessons that we learned from this as well. So the main areas that I'm going to touch on is storage and transport constraints for the vessel, the geometry constraints, performance constraints, and also our payload constraint. So early on in the design process, we ultimately looked to set our envelope for the design. And one of the main things we wanted to look at there was obviously our storage and transport constraints. That includes the vessel needed to be able to fit into a standard 20-foot ISO container. It needed to be road transportable by just a standard tow vehicle. It needed to have a standard footprint for shipping, allow for multiple units to be able to stack together, and also be launchable from a trailer or crane or davit. So one of the main design bits that we looked at there was how can we standardize the storage across the vessel for these constraints. So in the bottom left photo there, you can see the cradle that the EMAPS vessel is sitting on inside the container. That cradle is able to be just rolled straight out with the EMAPS vessel on it, lifted up, and then bolted down to a standard I-beam boat trailer. That boat trailer was one of the main constraints that we wanted EMAPS to be transportable quite easy. So we've kept the total towed weight of the vessel under 2,200 kilos. And the reason for doing that is that we wanted to make sure that you didn't need a special tow vehicle or you didn't need a special braking setup to be able to tow the vehicle. That same cradle obviously can then just be taken off the trailer, stored inside a warehouse with an EMAPS on it, on the back of a flatbed truck, or bolted onto the back of a ship. With that as well, I don't have a photo here, but we have a design and constraint in there that we wanted to be able to stack multiple units together. Reason we don't have a photo yet is we haven't had both the vessels in the same facility at the same time yet, which we're keen to do at some point so we can see how that works together. But effectively, it has 4 receiving points on the deck and 4 points underneath so that you can store 2 of them together on one cradle system. The vessel is also launchable just from a standard trailer at a standard boat ramp, and also from a crane or a davit. And you can see in the photo there, its first launch up at GCCM just using their boat lift. So performance constraints. So one of the key attributes of the EMAPS, it has the ability to stay on mission for a long period of time. So that obviously set out that we needed to make sure that we had a large battery capacity, and then also how were we going to be able to replenish that capacity while at sea. So that set out that it needed to be environmentally powered and make use of as much of the environment that it's operating in. And we've done that by having solar on board, which you can see in the photo there. There's solar on the deck, and then there's solar on both of the sails as well. We also utilize the sailing ability as well, which the boat can just sail on its own, or when the conditions are right and we can get a high enough speed, we can hydro regen with the 2 thrusters on the stern. This constraint obviously put us down the path of a lot of other design features, including making sure we had low drag, high stability, also needing to make sure we had a hull design that allowed for high command as well when sailing, which obviously is beneficial as well, as we had ambitions to make sure that we had a meaningful top speed and range and endurance. So after deciding on basically our design envelope of how are we going to store this thing and how are we going to operate this thing, we then set out with the geometry. We obviously wanted to make sure we had that reduced beam for storage inside a container and road transportable of 2.3 meters. but we also didn't want to lose the benefit of having catamaran design. So when it's deployed, we obviously have a beam of 4.25 meters. That set us down the path of making sure we had some retractable armors and retractable sails. The retractable armors use a armor retraction system, which is the first of its kind, that allows us to not only bring the hulls in, but also bring them up as well. Second to that, we also wanted to make sure that we were maximising our sail capacity on board as well, which meant we wanted large sails, but then again, we wanted to make sure we could keep it in that small, compact storage environment, so both the sails are able to be retracted and laid down fully. You see the communications mast there as well. That is quite a significantly large mast of just over 5 meters to make sure that we are getting up and above the sails so that we're not having any blockage effects or wooding effects on some of the sensors. But that also is able to just be lowered down and then stored into that same cradle design for container or road transport. One of the biggest design constraints that we had is obviously the displacement. Coming up with that displacement took a fair bit of time to make sure that we were maximising our displacement, but not pushing it so far that we wouldn't be able to tow it with a standard tow vehicle, making sure that we also had adequate room for all the electrical systems on board and battery capacity, which Michael can attest to was quite a challenge. And also making sure that we had a large payload capacity within that as well. So with payload, probably one of the most important features of any autonomous vessel is what can you do with it? And for us, that was one of the most critical things, was making sure that we maximize the amount of payload on board. So in that photo, you can see that there's 4 lids. Those 4 lids represent the payload bay that we have on board, which is 4.85 meters by 1.1 meter. That capacity is interchangeable, so any of those bins can be moved around, reconfigured to different sizes. All those bins have both power and data on board and are open to the air and also the water. Coming up with this obviously was a bit challenging. We constantly were pushing to see if we could get more payload on board, and then constant pushback as well to make sure that we're still leaving enough room on board the vessel for the other systems, especially the sail retraction system, which ended up being crammed in between there and then the sidewalls. So in summary, the main constraints of EMAPS is that it needs to fit inside an ISO container and be road legal. We also wanted to make sure that we were environmentally powered and using as much environmental contributors as we could, making sure that we had a significant payload capacity of 300 kilos, and making sure that we stuck to our 1,600 kilo displacement to keep it under 2,200 kilos for towing. We also wanted to make sure that the whole system was nice and compact for ease of storage. So what did we learn from doing the design over the last 2 years? The importance of setting solid design constraints early on, obviously making sure that we had that envelope that we were designing into. Also noting that maximising some of the design constraints will cause pressure on other systems, and we found that quite often with maximising our payload, we're putting a lot of pressure onto the other areas and systems on board. And also important to consider what we might not have identified yet in the future. There's a possibility of different use cases or different constraints, even from regulators in the future. So leaving some room for that. I'll now pass over to Eli.
All right, no chat, that's okay, good, I'm okay.
All right, so I'm going to be talking about kind of the differences between crewed and uncrewed vessels, and how that affects our design approach. So as Torsten said, EMAPS is a vessel that is designed to do short-term missions as well as long-term missions that can span over multiples of weeks. So this makes comparing autonomous vessels with crewed vessels very interesting because of the endurance characteristics between the two. So some of the key differences are pretty obvious, but they really do kind of shape the design approach to autonomous vessels. The first being no crew accommodation needed. So obviously there's no need for sleeping quarters, galleys, sanitation areas, hallways, and a lot of that volume isn't required in autonomous vessels. Second to that, there's also no life support systems required. So things like HVAC, potable water, and a lot of waste management systems aren't required. And to expand on that, autonomous vessels also have a different outlook on some of these kind of life support systems. For example, fire suppression systems, obviously very important on crewed vessels. It's there for safety, whereas on kind of autonomous vessels, the approach is very different. Obviously, there's not there to necessarily support life. It's there to protect the asset or protect the vessel. And it can be seen as a different outlook on these systems. Navigation and control. Obviously, there's a lot of dedicated area and a volume for this in terms of crewed vessels, whereas autonomous vessels, far less. For example, the bridge is obviously a really important area. And as Alan said at the beginning, the field of view out of the bridge is very important, whereas this is still true for autonomous vessels. And that's one of the reasons why we have such a high mast or communications mast to raise the cameras above our sail, kind of our sail line, and make sure that it doesn't shade any of our field of view. Quality of life considerations is also something you don't need to consider when you're talking about unmanned vessels. Stability, noise and vibration, and living spaces are all things that you don't need to consider. And this all adds up to a vessel that can be far smaller than a crewed counterpart, and optimized the design purely for the purpose of the vessel. And as EMAPS, as Torsten said, EMAPS is primary purpose is for that payload, and it's all been condensed around and that system. Again, that makes everything extremely dense and very system heavy in terms of autonomy. There we go. So weight attributes and how this affects our design. So weight tracking and weight estimates is obviously a very important part through all vessel design, and that's true, remains true for autonomous vessels. We were aiming for a payload capacity of 300 kilograms, which makes up a large portion of the actual weight of EMAPS. So it was important to try to maintain light construction and light components throughout the whole design and construction of EMAPS to maximize our payload carrying capacity. And that's, again, is dictated by our total trailable weight that Torsten mentioned. Not unique, but very prominent in the EMAPS design was the effects of moving weight on the trim. Because it's such a low draft and lightweight vessel, and the payload takes up a large amount of that weight, movements in the payload can have a large effect on trim. And unlike in crewed vessels of much larger size, where there's dynamic ballasting systems to compensate for these things, EMAPS doesn't have that, so it makes it a more of a design point or consideration where you're placing weights, and it's important to keep track of. Lessons learned, the importance of keeping track of all your weights. We, throughout the first design and commencing the build of the second design, we were keeping track of weights of individual components and full systems to ensure that we're meeting our targets and able to meet the performance criteria Torsten mentioned. And that's true with crewed or uncrewed vessels. And again, there's no consumables on board our vessel. So the issues with trim is also a positive, because there's nothing that gets drawn down through the full life of the vessel, so it doesn't affect trim. and passing on to Michael.
Thanks, Eli. So today I just wanted to discuss some of the key considerations for design and production of control systems related to unmanned surface vehicles and how that differs from the design of crewed workboats. My focus will be on control system design constraints specific to unmanned vessels and the effect this has on the selection of electrical equipment, as well as how that affects our installation considerations. As mentioned earlier by Eli, the challenges faced on control systems on USVs primarily comes from having no crew on board the vessel to manually control or override systems. So the absence of crew for us obviously a really big deal. This really leads us into the primary point where we need end-to-end control of all our systems via hardware and software. So, for example, on a crewed vessel, we might have a HMI interface or a switch that allows us to move motors back and forth, control our systems. On an unmanned vessel, we really need that to be software enabled. So that really leads to the point that sensor reliability and digital feedback of our systems is absolutely critical. So, for example, we have a sail retraction system, we have a rudder system, and sail rotation where they're all controlled by motors. Where we have a crewed vessel, we have visual feedback of those systems. An operator can look at the system, control it, and get that visual feedback. On a uncrewed vessel, we really need to get really detailed feedback from the motor itself. So it comes into the selection of the motor, getting encoder feedback from that motor, as well as supplementing that data with visual feedback, which we get from our cameras. So it was really important for us, given these things, that a great level of effort was put into camera field of view and making sure that we had good visual feedback from our systems. Given that we don't have humans on board as well, and all these systems are operated remotely, they all require power to replace the human operation. So one of the challenges on one of the biggest challenges that we did face was that this human control needed to be replaced by motors and systems that require power. So this leads to its own challenges, which I'll discuss later on. So following the above, it's a given that significant constraints are placed on the selection of electrical equipment. Space and weight is really the biggest driver. Generally, on crewed workboats, we have a crew there, as Eli mentioned. That leads to a lot of extra crew space, which we just don't have on unmanned vessels. So you can see in the photos that are on the screen there that the electrical system in the bow was quite condensed, really tight. We really had to be mindful of how we laid things out. One of the biggest spatial constraints that we did face was in the side hulls of the EMAPS vessel. The side hulls had a width constraint on the batteries that we wanted to install of about 180 mil, which really limited our option for equipment selection. While weight considerations are normal for any vessel, they became especially important for us due to the sheer amount of electrical equipment and cabling needed to give EMAPS the autonomy that we desired. I'll talk to this a little bit later on as well. So accessibility of equipment, because all the equipment is kept in enclosed spaces, accessibility was a huge challenge for us as well. You can see on the screen that we really tried to prioritize things like circuit breakers and our switching equipment, so that when we were working on autonomy development, those were the things that we really had access to when we needed them. So less focus was given on equipment like solar converters and the DC to DC converters, where the accessibility requirement for those was quite dampened. However, still desired in some respects, which I'll talk to later on. The big focus for us as well was power regeneration versus weight trade-off. We found that the solar panel versus battery trade-off was a big one for us. We found that if we were only out at sea for less than a week or so, it was better to replace solar panel weight with battery weight. But given the nature of the platform, it was obviously a no given that we'd go with solar regeneration, given we want the platform out for multiple weeks at a time. One of the other biggest constraints put on the electrical systems and the control systems was the aspect of modularity. As you can see on the screen there's a lot of connectorization going into the base of the vessel. That all comes from the mast. So we've got about 6 cameras, radar, AIS, VHF radio, UHF that we all want to be able to disconnect from the rest of the platform. So a really intensive labor activity that goes on with all that connectorization, but the net benefit for that modularity was definitely there for us. Same thing occurred for the dedicated power and comms infrastructure for payloads. 4 payload bins, all with 48, 24, 12 volts DC, power and communications. They all require connectorization to lean into that theme of modularity. So certainly a big design and labor effort, but the trade-off is that we maintain that modularity. So the autonomy system, it requires work, and given that it can't be done by a crew, it's done by motors and generators, which then put out heat into the rest of the system. It leads to an increase in power draw requirements. We have extra cameras, motors, control systems. We just have a generally more robust electrical infrastructure. Cables needed to be carefully selected to accommodate for the weight and space that we had. Cable routing was really critical for us. You can see in the photo on the screen, we have cabling running up from the battery banks and the side hulls, up the wishbone and boom to central distribution at the front of the boat in the bow. So there's quite large cabling coming across that space, and then the rest of the equipment fed from smaller cables from that central distribution point. Particular attention was also paid to the hotel loads of equipment. So just making sure that we had really low base loads of the platform, so that when we were operating at those base loads, the environmental regeneration was greater than what we were using, so that we essentially had a power surplus. That gives us the ability to go out at sea and operate for a longer period of time. With the increased power draw and concentration of equipment in the enclosed spaces, managing heat generation and dissipation was a huge design consideration for us. Components generating heat, such as DC to DC converters, the motors, require effective thermal insulation management to prevent overheating and guarantee a longer life. So here we implemented strategic decisions like heat sinks for the servo drives, strategic heat transfer through the platform skin into the water, and also considering the layout of equipment to optimize heat transfer through the platform. But this challenge really emphasised for us the earlier focus on accessibility and equipment layout, so maintaining ease of access to this equipment so that we can monitor heat, shuffle things around, and guarantee longer life of the platform was really important. So in summary, EMAPS was a huge challenge. Designing the electrical systems involved navigating constraints in space, weight, while ensuring that robust functionality was maintained. However, these considerations ultimately give us the best chance of success in the future.